getting started. Just a little reminder that we are at the end of the first 8 weeks. This is week 7. This is week 8. Okay, this is actually technically week 8. If you have second 8-week classes, it starts next week. How many people have second 8-week classes?
Right before spring break.
Hmm?
That's weird, right before spring break.
Yeah, that's how they schedule it, which is kind of weird. But since it coincides with spring break of my kids, I cannot complain too much. If it doesn't coincide, then it's a problem. Then I have to take time off or arrange, babysitting and stuff like that. All right, so we'll start with we'll go back to arrays first, and then I'll hand the test, back to you guys. Your test score once again is on Moodle already, so you can go to Moodle to check your grade. And I try my best to associate, the questions to learning objectives, like what you're supposed to learn. So when you look at your grade, it's kind of complicated because there are all these items, and then you can see how you do in each question with respect to each concept that I want to assess. Okay. Are there any questions at this point about arrays? Okay. Right. So we did this part already, initialization of an array, initialization algorithm. We did it last Thursday. Okay. So now we're moving on to section 5, which talks about how to search for a particular value in an array. In this case, we're dealing with an unsorted array. And for some reason, this is not showing up very well. So let's go ahead and see if I have another version of this that shows up better. Yep, nope, that's the only one. Okay. Because there's supposed to be a number here. So instead of reading the notes here, let us just go about doing it as an example first. Before you write an algorithm to do anything, it is always good to try to do it by hand first and see whether you can come up with a systematic way of doing something. Okay, so I'll give you an example, which is not going to be a very good example here. So I'll give you an example of an array that has the following values. It's not sorted. So we have 4, 7, 2, 10, and let's say 3. Okay. I want you to search for a particular value. In other words, I want you to tell me whether a particular value is in the array or not. 3. Is it in the array? Okay. How about 11? 37? 6? Now, did you use a systematic way to search for that value, or did you just eyeball it? You just eyeballed it, right? How do you write an eyeball algorithm? You don't.
Unless you've got a camera and a lot of time.
Well, you mean visually processing it, right? But eyeball algorithm basically means that we are doing something, but not in a very structured and systematic way. Okay, we just somehow grasp all the information and make a decision and say, no, 6 is not a part of this array. Okay, it's not one of these 6 numbers. Okay, so this doesn't seem to be a very good example. Okay, let's try to use an example that is a little bit more complicated, so you cannot just eyeball it. Okay, what about looking up the phone book? Okay, someone can immediately say, but that's stupid because a phone book is sorted, and you don't it's really easy. You just kind of flip the pages to the right one. But what if I tell you I'm not looking for a particular name? I'm not looking up by name. I'm looking up by phone number. Okay.
Tell you to use Google.
In other words, I'm giving you a phone number. I want to find out who owns that phone number in a phone book. How would you go about doing it?
I would.
Giving up is not an option. Yeah.
Have a version that you could manage on the computer, so you can just click start by number.
Yep. Okay, but if you are the computer, what are you gonna do? Yep.
Search from top to bottom first.
Searching linearly. Okay, so what you're describing is what we call searching linearly, which is a technical term of just sequentially one by one. Okay, why don't you look just randomly? I just flip to a certain page and see if I'm lucky.
This one.
You might go back and search the same item if you're just randomly doing it.
Because if it's exactly, and you don't know when to stop. Okay, because if you search randomly, okay, let's say you did that, repeat the same process, flip to a random page, look at a random thing, and say, oh, that's not the phone number I'm looking for. Let's say you did it 20 million times already. Can you stop? Let's say the phone book only has 10,000 entries, and you repeat this random process 20,000 times already. Can you stop? No, because you cannot be sure whether you looked at the same entry over and over again. Okay, so that's not a very good approach. The better approach is really just to spend the time, look it through one by one from page 1, and then go all the way to the end of the phone book. Okay, it's called linear search. Okay, so what linear search is basically starting with, well, guess what? The first item. If it is not what you're looking for, you move on to the next one. If that's not what you're looking for, you move on to the next one. But if it is what you're looking for, then you can just say, I can stop here because I have just confirmed that the value that I'm looking for is already in the array. Then you can stop, right? Okay, so how do we write an algorithm to do this? Okay, well, let's go ahead and use
Real quick before we get too far, did you start the recorder? I remember I saw you change something on it.
Yep, it is. Good idea. Double check. Okay, so here is a little notepad here. We'll do the same thing, of how to, constructing our algorithm, but step by step, without, going from the first line all the way to the last. Okay. So here we're going to write an algorithm to search an array linearly, which basically means sequentially, for a particular value. Okay. So just like usual, we start with revision 1, and it can be extremely vague. Okay, revision 1. Yep, go ahead.
This algorithm can be numeric or alphanumeric. Does it matter?
The values that we're comparing?
That is
Okay. Okay, so the first thing we want to do is to look at the general structure of the algorithm, and we have to kind of decide between two things, or three things. One is, it is just a sequence of operations, one after another, with no going back and no branching. The second one is, it is a branch, okay? We go to it at a certain point, we make a decision, we either go left or we go right, and then, from both sides we are done, okay? There's nothing else to do. The third one is saying, well, there's some kind of repetition here, okay? We're doing the same thing over and over again until something is true or until something is false. So out of those three options, which one do you think will fit what we were doing with the phone book? Is it conditional? Is it just a straight sequence? Or is it a loop? Is there any type of repetition involved?
Yeah, it's a loop aspect.
Lots, right? Yep.
Make those numbers more insequential. So you can say if does this has this set string of numbers or look at it. Or if it's not this first string of numbers like the array code, you can skip those.
But it is still a loop, though. I mean, because you
Like get rid of it by pre-checking it correct.
Can you say again? Because the blower is kind of loud.
You could pre-check the numbers for conditions, so you can skip like a set of numbers. If it was like 916 in the area code and you're looking for 952, you can skip those with the conditional statement.
But in the phone book, it's not sorted by phone numbers.
Well, we can have a list that was sorted that way, or we can doing it by
Right. If the array is already organized in a certain way that relates to the value that you're searching for, yes. But in this case, since it's not sorted in any way, which also implies it's not organized in any way, then you cannot apply those techniques. But that's a good idea. That's a reason to organize things, so that you can retrieve and locate items more easily. I do not understand why they would pick this kind of time to blow leaves.
Why not? This is why not.
Because a leaf blower is about 120 decibel.
I think he heard you. This is going to sound great on the video. All you're going to hear is...
You could just type out everything you were going to say.
Oh yeah, that's right. I can just type it out. Okay. The moment I try to talk about something important, they're going to crank it up, right? Okay, so we know this is some kind of a loop, okay? We have to repeat doing something. And when do we when do we exit the loop? When can we say, okay, it's time to stop because we have a conclusion of some kind?
When we find a value.
Hmm?
When we find a value.
When we find a value, okay. So we'll say when we find the value. Is there anything else? Are there any other reasons for me to get out of the loop? In other words, in the case of a phone book, what if I go through all the entries and flip all the way to the back of the entire phone book and go, it's not there. Yep.
If you have a specific count number, so you can increment for how many entries you have, you can increment by one, and then if it reaches a certain amount of entries, if you have 10 entries and you go to the 11th entry, you can exit because you don't have it
Okay,
there.
you're right. But in this case, we are trying to describe, what that really means. So, so you got the mechanism already. You're way ahead of me. I'm just trying to determine how do I describe that other condition that let me get out of the loop. Okay. When there are no more. Okay. So or there are no more entries. Okay. All right. So that's fine. Okay. Yep.
Do we want to say no more entries, or do we want to say no more similar entries? Or it doesn't matter?
There are no more entries to compare, I guess.
Okay.
Yep. So no more entries to compare. Or you know what? The other way to say this is there are no more candidates. Okay, because each phone number that is not compared yet is a candidate because it may match the number that you're looking for. But if there are no candidates, which means you have compared the value you're looking for with all the entries and they're not matching, that means you have no candidates left. Okay, no entry left in the array can possibly be the value that you're looking for. Okay, no soft drink. Sorry, because I don't want any sugary stuff on the carpet. Thank you. All right, so that's a good way to describe it. Okay, so we'll start with revision 2. In revision 2, instead of saying the value, the entries, or the candidates and stuff like that, maybe we should start to use names of variables. Okay, because that really makes things a lot easier to understand. So we'll just say, assume k is the value that we are looking for. And we can assume A is the name of the array containing the candidates entries. So I'm just using names here. Okay, so let's see how much that can help me. All right, we find the value. Oh, great. Okay, but can we express we find the value using the terms that we have introduced? Okay, well, we know that we're looking for the value k, and we know that we are matching it to something in A, right? A is an array, and matching means they are the same. But this doesn't work because k equals A is comparing k, which is a single value, to A, which is an array. What is an array? It's a box, okay? I cannot compare a single coffee mug to an entire box of coffee mugs. I can compare it to one of the coffee mugs in the box, right? So that means I need some kind of index in here, okay? And since I don't really know how to specify the index, I'll just put a question mark there and say, I'll figure this out later. So in other words, this condition is now replacing this condition here because it's a little bit more specific, even though we still have some fuzziness about it. The other one is there are no more candidates. Okay, we'll just say that there are no more A bracket something to compare to. Okay. It's still better than saying there are no more candidates, because now we are saying, okay, there are no more elements in the array to compare to anymore. In revision 3, we look at the question mark and say, well, can we replace the question mark with something, so that we can make this more meaningful? Well, let's see here. We'll go ahead and assume that a particular variable, let's call it I. Assume I is the index of the element that we are examining, or comparing if you want. Okay. In other words, since I can only look at one particular entry in the entire array one at a time, I'm using a variable I to control which one I'm looking at in each iteration. Is that okay? All right. So in that case, the first condition becomes a little bit easier. I can actually finish that one off by saying if k equals a bracket I, then I can exit, because that means a particular element in the array has the value k. I confirm that the value is in the array, I can exit the loop. I can make that conclusion. But the other one is still a little bit difficult to explain or use I for. No more a bracket I to compare to. We'll leave this one alone like that one, but like this for now, since we don't really have an idea of how to do it just yet. In revision 4, we want to incorporate how are we going through the entire array. In other words, am I making I a random number for each iteration, or am I using I in a very systematic way so that I'm going through the array using a particular pattern? Because up to this point, if you look at revision 3, I didn't tell you how I gets its value, right? So I can be saying I gets a random value for each iteration. And then you go back to the whole thing of, okay, we just flip to a random page, look at a random number to see whether it matches or not. And there's no way you can exit, because you can never know whether you have gone through the entire phone book or not. But we want to do it the more systematic way, which means we want to start from the beginning, and then we go for the next one, the next one, the next one, until we either find it or we get to the back, all the way through the phone book. Okay. So using that particular method, what do you think I should start with? It should start with 0, right? Because that's the first entry in the entire array. Okay, so that's good. Okay, and we have to put this initialization before the loop. So we copy and paste the loop here. And what am I? Okay, let's not worry about that part. Okay, so now that we know, okay, so I'm just writing down some comments here. I starts with 0, and it increments. All right, so given that this is how we are changing I, can we use I to indicate that there are no more elements to compare to? How should I say that?
That's great.
Go ahead.
You say like in minus I, in being the number of possible values we have.
Okay, so that means when I is greater than or equal to bar a bar, that means it's no longer a valid index. Does that make sense? Now equal to is good enough, but greater than or equal to doesn't hurt. Does everybody understand why when I is, okay, I starts with 0, and I'm going to increment I when k does not equal to a bracket I. But if I keep adding 1 to I, eventually it will become greater than or equal to bar a bar. That means I have gone through every single element in the array and still could not use the first reason to get out of the loop. But if I have gone through all of the elements and still could not get out of the array using the first reason, which is I just found the element, it means that none of the elements in the array matches the value k. Yep.
So bar a bar is the max value for this array.
No,
Or the last element.
it is the number of elements in the array.
Total number of elements.
Yeah, the number of elements has nothing to do with the values of each element. It has to do with the number of elements in the array. So I have 20 coffee mugs in a box. but I don't really care about the content, in each coffee mug. I'm just counting the number of coffee mugs. All right, so this seems to be okay. Now it has a fundamental flaw. We'll find out what that flaw is, and then we'll use that to kind of talk about a very important part of programming, especially in C and C++. Okay. We just have to fill in this part here. What do we do in the loop? In other words, what are we doing for each iteration? Well, let's take a look. Go ahead. We need to do an increment for I. In other words, this is my exit condition, right? We have been working on the condition that tells me that it's time to stop, and we can get out of the loop. But in order for this to eventually become true, we have to change k. We have to change k elements in array A or I, right? Because those are the three names referred to in the expression. Is that making any sense? So if I want the entire expression to become true over time, that means something has to change. I can change k, I can change an element in array A, or I can change I. Does it make any sense to change k? In other words, you gave me a number to look up in the phone book, and I come back and say, well, I don't know about the number that you gave me, but this number is in the phone book. Is that answering your question? No. Okay. So I cannot change k, which is the value that I'm looking for. Can I change the entries in the phone book? You gave me the number 555, 5555, and I look through the phone book and go like, I don't want to go through this trouble. I bring out my little whiteout, I erase the first entry in the phone book and turn it into 555, 5555, and they say, yep, it's in the phone book, I'm done. Is that solving the problem? No. So I cannot change elements in the array. That only leaves one thing to change, which is which entry am I looking at in the phone book? That's the only thing I can change. Does it make any sense? I'm narrowing down which part of the expression I can change, and that helps me decide what I need to do in the loop. Okay? Now that I know that I cannot change k, I cannot change any element in array A, can I make array A bigger or smaller? In other words, can I just kind of burn the phone book and say, what phone book? Of course that entry is not in the phone book. No, I cannot, right? So because that's another way to make this loop exit is to basically delete all the elements in array A and say, array A has 0 elements. I'm done. But that's not answering the question, right? So the only thing I can change is I, and I starts from 0. I want I think I has to eventually become a bigger and bigger and bigger number until it is greater than or equal to bar A bar. So what do you think I need to do for each iteration so that is what we are going to do?
Increment I plus.
We increment, yeah, exactly. I gets I plus 1 is what we need to do in the loop. So if we are staying in the loop for each iteration, we are bumping up the value of I by 1. Yep.
Would you have to say it starts with -1 as to initialize on 0?
No, it's okay because loop and loop does not indicate whether it's a pre-checking or post-checking.
Okay.
It simply says it is a loop of some kind. We'll have to decide whether it's pre or post later on. Okay, whether it's pre-checking or post-checking, but at this point we just want to identify that we have some kind of loop in it, and this is where we can get out of the loop. Okay, because I don't want to be bogged down with that kind of details initially. When I have the entire algorithm done, then I can decide, am I forced? Do I have to go through at least one iteration, or can the condition be true? Excuse me, I take it back. In the while loop, can the condition be false to begin with, so I don't even have to perform one iteration? Okay. So that's where we are at this point. So we are now going for revision 6. Now when you move on to CISP360, this is the algorithm design part of this class. Okay. Now the tracing part has to do with the mechanisms. Okay, we're working on the actual mechanism of how things are done. But when it is about how to design an algorithm, this is how I do it, okay? Or this is the best I can describe the process of designing an algorithm. All right, so in revision 6, we basically have an option to turn it into either pre-checking or post-checking loop, okay? And you can do it either way, okay? 6a makes it a post-checking loop. So as a post-checking loop, we have to do exactly what you said. We have to turn I to -1 or initialize I to -1. And then we say repeat, I gets I plus 1. And then we say until k equals a bracket I, or I is greater than or equal to bar a bar. And then in revision 6b, which is the alternative to this particular algorithm, we initialize I to 0, and this time we use a pre-checking loop that says, while the inverted part of this, the inverted version of this condition, which basically says, as long as k is not a bracket I, and I is less than bar a bar, do I gets I plus 1, and y. Okay, this condition here is the negation of this condition here. In other words, the other way to say this is simply to copy and paste this thing, the entire thing, and then say it is not blah blah blah. Okay, I already applied De Morgan's law to convert everything like this one. The negation of this becomes this. I applied De Morgan's law, without actually spelling it out. Does that make sense though? I mean, you want to stay in the loop as long as the element that you're looking at is not the value, does not have the value that you're looking at, and you're not at the end yet. That's the condition to stay in the loop. All right. So out of the two, which one do you think is better? They are equivalent. The second one. Okay. The second one is better because it spells out more clearly what is the first index that you'll be using for the comparison. Yep.
Also, depending on what we're doing the actual first interesting time, correct?
Mm-hmm. Yep. All right. So we are almost done here. It's time to trace the algorithm and see whether it works or not. Okay. So we'll switch to a spreadsheet. Not this one. I suppose we can use this one. Just get rid of this. It's not really that useful. All right, so we'll just go ahead and use the same algorithm. I forgot to turn off autocorrect. So we go to turn off everything except for replacement table. And we look for I. Entry. All right, so I gets 0, while k does not equal to a bracket I, and I is less than bar a bar, do I gets I plus 1, and while representation here. Here we have our loop. In a separate window, we will trace it. Okay, there we go. Because we have a condition to evaluate, we need a comments column. It's going to be wider too. We have line number, we have variable I, variable k, and variable a, which is an array. These do not need that much space. We'll just make them smaller. A, on the other hand, is an array. I don't really want to bother myself with a really huge big array because to illustrate the point that I'm going to make, I just need a tiny little array, maybe an array with one element. Okay, that's good enough already for this one. So the first element has an index of 0, and it has a value of 6. Okay. Does everybody understand the difference between the index of an element in an array versus the value of an element of an array? The index is kind of like the name of the entry in an array. It identifies a particular element in an array. the value is basically just what it is storing. The value can be changed over time. So we start with the value of 6 here, and let's just say that we are not looking for that particular value. I'm looking for a value of 3. I does not need any specific value to begin with. It can be unknown, and this is my precondition. Because what I want to do is to illustrate that this program has one big flaw, okay? And it has something to do with something that we talked about last time. On last Thursday, do you still remember what we talked about? When we try to access an array with an index that is out of the range, do you still remember that? There are 3 possible cases, right? In C and C++, it will silently do something that's wrong, sneaky, okay? In VB, it screams at you and say, you're not supposed to do that, stop. Okay, and here's the line that is offensive. And then 3, in PHP and Perl and many other scripting languages, it will say, oh, I want to please you, okay? If you want element 256 and it's not in the array yet, I'll make the array bigger so that that element starts to exist, right? Okay, so remember that problem, and then now we can see whether we have similar issues here, which doesn't seem to make any sense. Why would we have similar issues here? We have the bound checking here already. I is less than bar a bar. I mean, that seems to be a pretty good bound checking to make sure that I makes sense, and I start with 0 and not any negative value. How can we end up with something that is bad? All right, so we'll go through this algorithm once, and we'll see why bad things can happen here. Okay, line number 1, okay, I gets initialized to 0, no big deal here. Line 2, we evaluate the condition. K is 3, we compare that to a bracket I, but since I is 0, we're comparing to a bracket 0, which has a value of 6. K is 3, a bracket 0 is 6, 3 is different from 6 is true. Okay. And since we have a conjunction, we have to evaluate the other side too. I has a value of 0. 0 is less than bar a bar. What is bar a bar in this case? How many elements do we have? We got 1 element. Bar a bar is 1. 0 is less than 1 is true. Okay, so no problem. No problems whatsoever here. This entire thing is true. We go into the loop, go to line 3, we add 1 to I. Now we go back to line 2. And then we compare k to a bracket I. What is I again? At this point? 1. Where's a bracket 1? Does not exist. Okay. We have a problem. Because right when we try to compare k to a bracket I, those problems that we mentioned last week will come back. Okay. In other words, in C, it will just go to, in this case, column F and say, I'll just compare k to the value, whatever it is in column K, and give you the result of the comparison. Okay. In Visual Basic, the program will stop. It will give you a dialog box and say that you're accessing an array out of bound. In Perl and PHP, it will create enough entries in the array so that a bracket 1 exists with a particular initial value, which is a nil value, which also can be compared to 0. Okay, but none of those 3 things are what is supposed to happen. Okay, so now we have a problem, because even though we have a condition, which is I is less than bar a bar, to try to keep track and make sure that I is a valid index, we did that comparison too late. Because we encountered the first condition first, which is k versus a bracket I, we already ran into the problem. So the second condition does not even get a chance to evaluate, because the first condition is going to cause the problem first. So how do we solve this problem?
More code. More code.
Sorry?
We need more code.
You need more code. Yeah, well, it depends. It depends on whether you want, oops, come on, know how to save a file. Okay, in this case, the issue has to do with the ordering, not just the ordering, but also has to do with, that doesn't work for some reason. Today is 12. Just can't type today. I should have a script to do this. A script that runs, and it compares today's date and time, and then it knows what file to create and start the recorder and the whole thing. And it will detect my presence. If I'm missing, it will start to replay, like a screen recording from last semester.
Do you need a camera for that? You need a camera?
No, just a screen recording. You can just pretend that.
In order for it to detect your presence.
Oh, to detect my presence?
Yeah.
Or a pressure sensor.
Pressure sensor is cheap and works well.
Or you can just use the mic and use the audio
Eye sensor?
sensor. The audio with the mic, you can do a voice sensor.
Yep.
Voice recognition.
Kind of. You can do voice recognition. So I'm going to save this file. Okay, we'll save bad linear search. Okay, so this one is bad because it causes a problem. I'm going to save the file again, this time as good. Okay, there are several ways to solve the problem. The root of the problem is this is a single condition. Let me just highlight the part here. This is a single condition. You cannot separate the two parts. You cannot say, well, I only want to do the comparison of k versus a bracket I only if I is less than bar a bar. Okay? Well, at least at this point, we don't know whether we can do that or not. But because this is an expression, and conjunction is symmetric, right? It's supposed to be commutative. In other words, A and B is the same as B and A. It's just like with addition or multiplication. A plus B is the same as B plus A. So I'm supposed to be able to flip the order, and the thing is supposed to work. So we'll go through the first, which is the more difficult way to solve this problem first. We'll go through that method, and then we'll go back to the simpler method to solve the problem. One way to solve the problem is to introduce an additional variable so that we can separate the evaluation of this part of the expression from the other part. So this way, once they are separate, then I have a way to make this program work. So I'll go ahead and make this change first. So what I need to do is to say I have one variable called found, and it starts with a value of false. What? Can we do that? I mean, up to this point, every single variable, including elements in an array, they always contain numbers. And now I'm saying, oh, guess what? You can make a variable and you can initialize it to a value of false. But true, false are not numbers. I mean, they are Boolean, what we call Boolean values or true, false values. Is that really okay? Can variables, store true, false values? And the answer is yes. Okay, you can definitely do that. Okay, so that's how we're going to solve the problem. Because what we're going to do is we'll change this program and replace only this part to the variable found, or not found, I should say. Okay. So while not found and I is less than bar a bar, keep doing this. Well, but this is not going to be very helpful, because if you just analyze the program as it is right now, okay, let me just spell out what the problem is. I want this condition to be eventually, false, but inside the loop, nothing is changing found, right? At this point, nothing is changing found. So I know that something is not right about this program, because inside the program, I'm supposed to do something about found here. Okay? Let us think about this a little bit here. I want found. Well, found has a name of found. Why do you think it is named found?
Changing the value because there was a comparison made.
it's the result, it's a conclusion, right? It's basically telling me whether the value that I'm looking for is found or not. It is false to begin with because that's before I performed any comparison. In other words, if I just give you the phone book and the number, and I ask you, is the number found? What would be your answer? You can say, I haven't done it yet, okay? But if I demand a true-false value, and I ask, have you found the number? Your answer will be false, okay? I have not found the value. So that's exactly why found is initialized to false. Okay, so here we will have a way to turn it into true, okay? So we'll go ahead and do it the long way, and then we'll go back and do it the short way, which is a lot shorter, okay? The long way is the obvious one, the short way is the really, really, elegant one. Okay, the long way is really just saying, if A bracket I equals to K, then found gets a value of true, otherwise found gets a value of false, and if. And let me fix the indentation. I will fix the line numbers later, okay? So right now we just focus on the logic of this code. Is that making any sense? I want found to become true, but only if I can confirm that an element in the array has the value that I'm looking for. And this gets the job done, right? Okay, because the comparison A bracket I equals K is true if and only if I found that one element in the array that has a value of K. And if that is the case, I'm just changing the value of found to true. If it is not, I'm changing the value of found to false. It's false to begin with, but it's okay to make it false, 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 false again. It's not going to be a problem. Okay, so this is one way to write the program. Okay, but I will tell you that this is the long way, and it's really a lot of this is unnecessary. I can compact these 5 lines into a single line, and it makes more sense. Okay, so let's take a look at the second version. I will not erase this so that you can compare. Okay, so here comes the second version. The second version basically says, well, out of these 5 lines, 4 are unnecessary. Delete these rows. With the one that is remaining, we just say found gets the result of the comparison of A bracket I equals K. Does it do the same thing? Well, let's think about it, okay? A bracket I equals K is a Boolean expression, which means it can either be true or false. So if A bracket I equals K is true, the first version of the program will put true into found. Is that right? What about the second algorithm? How is it going to change found? Found becomes true. True, because A bracket I equals K is a true statement. So this is okay because this is just like any other assignment statements. How do you deal with a general assignment statement? You evaluate the right-hand side. Whatever the value is, you use it to change the left-hand side. Remember that? Okay, that's basically how every assignment statements work. So with this particular assignment statement, we evaluate the right-hand side. In this case, the right-hand side, A bracket I equals K, does not give me a number. Instead, it gives me a true-false value, right? I take that value, and I use it to update the variable on the left-hand side. In other words, it works the same way as found gets 2 times A bracket I. Okay, it doesn't matter because whatever the value is on the right-hand side, it is going to use it to update the left-hand side. Yep, go ahead.
I just have a quick question. It's like, what if the value you're trying to find just happens to be the last value in the array?
It'll work. It will still find it.
But even if you add I to I plus 1, and when you go back, it's no longer, because now I would be equal to
But
A.
found as a variable will reflect that you did find it.
Right, it'll say true.
Right.
But because it's a conjunction, don't you need both of them to be true to exit the loop?
That is true. No. Okay. You need both to be true to stay in the loop. Because this is a while loop, it's a pre-checking loop.
Oh, okay.
So you need both conditions to be true to stay in the loop, which the other way to say that is if at least one side is false, you get out of the loop.
Yeah.
So this works out because if found is true, then not found is false, and that will get you out of the loop. Okay? So this is one solution. Okay, this will work. In fact, it is kind of nice because when you get out of the loop, the variable found is the conclusion. If it is true, it means the value is in the array. If it is false, it means the value is not in the array. Okay. Cool. All right. But what if I tell you there's another solution that's even simpler? Okay. So I'll give you the solution first, and then I'll explain why it works, because it seems like it should not work, but it does. Okay. So the other solution is I get 0, okay? But I don't even bother with found anymore. Instead, I reverse the order of the two comparisons. I compare I to bar A bar first, and then I compare A bracket I to K. Okay. All right. So we'll go ahead and look at this code and go like, wow. Well, we looked at this code before, except the conditions was, the two side of the conjunction was reversed earlier, okay? And now it is, the other way around. How can this possibly solve the problem? We'll go ahead and find out how this will solve the problem, okay? Using exactly the same test case. So here I will number the lines and go to the other window for a trace. And pretty much I'll go ahead and erase enough of it. So we start with line 1. Line 1 is just initializing I to 0. Okay, no big deal, we know how to do that. And this is line 2. In the first iteration, or the first time we evaluate, it's the same thing. Because I is 0 at this point, bar A bar is 1. 0 is less than 1 is true. Evaluate the second side, the other half. A bracket I is A bracket 0, which is 6. 6 is different from K, which is 3, is true. So A bracket I is different from K, is also true. True and true is true. We go into the loop, we go to line 3, it adds 1 to I, and then we go back to line 2. So we will say, but shouldn't we end up with the same problem as before? Well, we do evaluate from left to right, okay? So in this case, we evaluate I is less than bar A bar first. What is I? I currently has a value of 1, and bar A bar is 1 as well. 1 is less than 1 is false. With a conjunction, if I know that one side is false, can I conclude the entire thing is false?
Yes.
Yeah. I can, okay? And being lazy as I am, I just say it's false, and I'm out of the loop, I'm done. In other words, because I'm lazy, I stopped myself from stepping on the landmine. Okay? There is a name for this technique. This technique is called short-circuited evaluation. In other words, in the case of a conjunction, if the left-hand side is false, you don't bother to evaluate the right-hand side. Is that making any sense? You can also apply the same technique to disjunction or, except it is flipped. If the left-hand side is true, then the whole disjunction has to be true. So you don't bother to evaluate the right-hand side. That is short-circuited evaluation. You look at this technique and you go like, that seems like a hack. It seems kind of kludgy. And it is, okay? It is a hack, it's kludgy, it is kind of more or less like a shortcut. But you know what? It is also specified in the ISO standard of C and C++. In other words, no matter which compiler you use, no matter which platform you are programming, when you write a program in C and C++ and Java the same way, Perl the same way, it is a part of the specification of the language. The conjunction and disjunction has this feature. It always evaluates from left to right. And if it can conclude the result of the entire operator, it won't bother with the other side. Yep.
Can you pull up the bad line search file real quick?
Sure. Absolutely. Let me save this one first, and then we'll bring the other one back up.
And keep that one on the screen.
Sure. This one is bad. This one is good. The only difference is the ordering of the comparison. It saves you a lot of trouble, because if we did not have short-circuited evaluation, we would have to use this method, introduce a new variable so that we can isolate the two parts of the conjunction. Yep.
That one's bad because of semantics, right?
No, the bad one is bad because of the ordering of the evaluation. Because when it comes to conjunction, the compiler makes sure that we always evaluate from left to right. And whenever it can conclude the result of the entire operator, it stops. It does not evaluate unnecessarily. So that's why it makes a difference, because in this case, if I is no longer less than bar A bar, it doesn't even bother to evaluate this side. So we will never index out of bound. But in the other case, we attempt to compare an element in the array first, and then we say, oh, by the way, is that index within boundary? It doesn't work because the ordering is always left to right. Yep.
So because of our human thinking, that's why the bad line search doesn't work. I mean, as far as the way the computer evaluates it.
Correct. Now, if you present this to a mathematician, like a math professor, the math professor will not be able to tell that these two versions should make any difference, because in mathematics, conjunction is commutative, which means A and B is the same as B and A. So if one breaks, the other one should break as well, because both should be invalid. But in programming, because C is quote unquote kludgy, okay, it includes hacks like that to improve the efficiency of a program. It does make a difference which one is on the left-hand side and which one is on the right-hand side, because the evaluation always goes from left to right with a conjunction.
Common thought error that comes up constantly in programming, or is this one of those unique situations? Not unique, but rare.
I'll put it this way. This feature, which is called short-circuited evaluation, which is also sometimes called lazy evaluation, is in the specification of C, C++, Java, Perl, PHP, and just practically all languages derived from C. But there are programming languages out there which do not have this specification. Like Pascal, the original Pascal says it always evaluates both sides of a conjunction. Okay, so it makes a difference. It's a very subtle one, but it makes a difference. In Visual Basic, I think you can choose to be lazy or not, because if you want lazy, it is by default. If you use and, it is by default lazy. But if you say and also, then it is not lazy. It always evaluates both sides. In fact, let's double check and confirm that, because I don't want to give you guys wrong information. So we'll just look it up real quick. Visual Basic and also. Okay, and also performs, okay, I got it the other way around. In Visual Basic, if you just use the word and, it is not lazy. In other words, if you use the word and, it always evaluates both the right-hand side and the left-hand side. If you use the word and also, then it is lazy. If the left-hand side is false, it doesn't bother with the right-hand side. Okay? Which is really kind of, it's really bad for programmers, because a regular and in most other languages is short-circuited. So if someone is coming from a C and C++ background and try to write a program in Visual Basic, this kind of thing will be a problem, because it is just not how the standard of other languages are specified. Okay. So do we have any other questions about this particular program? Let me just show both of them at the same time. Yep, go ahead.
So which one would be the more appropriate one to use, the first one or the second one?
You mean in the correct solutions?
Yeah, the correct solutions, or the,
Okay.
sorry, the second or the third one.
Okay, so in the correct solution, you're asking whether we should use this solution
Yeah,
or
which
this
one would be
solution.
preferable?
That's a good question, and the answer is somewhat conditional too. If you want a universal algorithm that works in all programming language, this will work. Because this will easily work in both cases, because whether it's short-circuited or not, okay, let me put it take one step back. This version will work whether it is short-circuited or not. So it's more universal. But this solution is more efficient and is more common in C and C++ programming. So in C and C++ programs, you will see this approach all the time. This is how people are, what people are used to, but it's definitely not universal because if you're translating a program into VB, this you have to be careful because now you have to remember to use and also instead of just regular and. Okay, so that's a good question. It depends on whether you need to port the algorithm to a variety of languages. If you think that you need to do that, the first version, or lines 12 to 17, is more universal. Yep. Have you run into that problem before?
Yeah, no.
No? Because that would be a kind of weird problem to run into, because the program looks right, but it's not because of the little things that are specified in the language.
And that would be really hard to find too.
Yes, it is extremely hard to find. Yep. Yep.
For all of this, like code conversion and stuff, from going from Python to some other language, is there any kind of like a script to autocorrect some of the like syntax or something like that?
Well, the syntax can be checked, and they can tell you something is wrong, but usually there's no autocorrect, which means it knows that you have a syntax error. It can, when you have a syntax error from a compiler or an interpreter, depending on the tool, sometimes it gives you a quote-unquote cryptic message because it's looking at things from the perspective of the parser, which is the component inside the compiler to try to analyze the code that you have written. So that error message will be kind of cryptic because it's not really looking at things from the human perspective, but looking at things from the compiler's perspective. Some compilers these days will give you a suggestion. So in addition to telling you the cryptic message from the perspective of the compiler, it will also give you a hint like most of the time this happens when people make this kind of mistake. So they tell you where to look for problems when you have a cryptic error message. None of the compiler that I know make suggestions to say, well, this is the problem and you want or autocorrect, which means it does the correction without even letting you know. So none of the programming languages that I know has a feature of autocorrect. Yep.
So it does syntax correction, but not logic correction.
Right. In this case, it's a logic issue. The reversal of the two sides of a conjunction is not a syntax error. Okay, they are both syntactically correct, but the behavior of the two versions are different.
And without doing a trace, we wouldn't have caught it.
That is correct. Yep. All right. So are there any additional questions about this code? No questions? Now what if I throw you a bone and say, what if I tell you the array is sorted? Can you improve a sorting algorithm? Okay. How would you improve an algorithm? Now, in this case, the easy way to improve the algorithm, if I tell you the array is already sorted, one easy way to improve the algorithm is simply to change this to one way, because depending on how the array is sorted, you can get out of the array pretty early if what you're looking for cannot possibly be in the rest of the array. Okay, let's see whether it makes sense or not. Let's say, okay, I'm just using sheet here to illustrate that point. Cool. So we're dealing with an array that is sorted in a non-decreasing way. In other words, it's increasing, but you can have duplicate values. So we have 2, 4, 7, 10, and let's say 14 here. Okay. I'm looking for the value 6. Okay. I'm still doing linear search. So here we can say, 2 is different from 6. We have to continue. 4 is different from 6. We have to continue. 7 is different from 6. We don't have to continue. Because if what I'm looking for is, if the array at this point is greater than the value that I'm looking for, and the array is sorted, what is it telling you about all the other elements that I haven't looked at? They're all greater than the value that I'm looking for, which means I can exit early. So this is one little optimization you can put into linear search, but this is not really nearly the best linear search. This is not the best you can do with a sorted array. Okay. So let's go ahead and switch gear a little bit here, and I'll just give you some numbers, and you can basically tell me what you think of. And for this part, I can use mouse pad. Make sure I save the file first. What is the world population right now? 7 billion. Okay, give or take, but not quite 8 yet. Okay, so we have a world population of 7 billion. Okay, 7 followed by 9 zeros. That's a lot of people. And let's say I have a universal book, of everybody on Earth. Okay, and each person is assigned a particular ID number, and I'm only looking up people by ID number. So the array is sorted by ID number, and I'm using ID numbers to look up a person. The question is, how many comparisons do I need to confirm that a person is not in the directory? That's the question. I have a directory that is sorted with 7 billion entries. I want to confirm that a particular entry is in or is not in the entire catalog. So the question is, how many comparisons do I need? Go ahead.
You only need the number of comparisons up to their ID number.
Up to the
And
ID
plus
number
one.
plus 1. Okay, so that's one way. Yep.
Are you saying it's in or out, not specifically finding it, because you only need one, then you only need to check if it's in the range of your 0 to 7 billion.
Okay, but what if I don't give you any constraints of the value that I'm looking for? In other words, I'm not telling you whether it's within the first, what if it is smack in the middle? In other words, what if there are 2 entries in the middle of the entire array, and the entry I'm looking for is right between them? Then you cannot apply the technique of looking at the first one, the last one, and say, oh, this is less than the first one, toss it out, or it's greater than the last one, toss it out too. In other words, I need an approach and also a number of comparison that will work for every single case. So not just special cases, but every single case. And the number is,
10. Can we check every digit?
That requires a special organization in the array, which means you have to. It's no longer a sorted array. What you're talking about is a tree, where you basically look at the first digit, it splits it into 10 little bins, and you look at each bin, it's split into 10 little bins. So in that case, yes, in 10 comparisons or whatever the number of digits you have, you can confirm whether something is there or not. But it doesn't work in general in a sorted array, because the array may have things that are not. This approach does not work. Okay. All right. Does anyone else want to guess? General purpose, search algorithm that will work whether you're sorting by name, by ID number, or whatever you want to use. Drum roll. 33 comparisons. Which sounds kind of really unrelated to 7 billion, does it? Until you use the log of 7 billion and you compare that to the log of 2. let's do that. Okay. So we'll go ahead and use a calculator. So let's see, calculator. Bring it up. Switch mode to scientific. Advanced. Okay, fine. All right. So we look at the log of 2. Okay. So we have natural log of 2. 0.7 or so. Okay. We look at 7 billion. 7, 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, we want to look at the log of that, the natural log, and it's 22.66. Okay. So what is 22.67 divided by, what was it, 0.7 or so? It's a number where the ceiling of this number is 33. Okay, so why is that working out? It's because in binary search, this is the way it works. Okay, so let me describe binary search in general first, so that you can kind of grasp the general idea of binary search. Binary search only works in an array that is already sorted. Okay, instead of starting from the beginning or the end, we start from the middle. So out of the entire stack of 7 billion cards, okay, you pick the one that is right in the middle. You take that one out. You compare that to the number that you're looking for. Based on the comparison, 3 things can happen. 1, you're super lucky. That's the number that you're looking for. Very unlikely. Okay. More likely, the number that you're looking for, the one that you pull out of the stack, versus the number that you're looking for, is either greater than or less than, right? But it doesn't matter which way, because if it is greater than, you throw away the other half. If it's less than, you throw away the earlier half. Okay. And then what do you do with the rest of the stack? You cut it in half again, and then every single comparison, you get rid of 1/2 of what is remaining as candidates. With 7 billion to begin with, in 33 comparisons, or in 33 division by 2, you're down to 1 single card. And that's why 33 comparison is what you need to look for a particular entry within 7 billion, assuming the array is sorted. What if I have 14 billion? What if world population doubles? How many comparisons do I need? 34, exactly, because in one comparison, I cut 14 billion back down to 7 billion. And I already know that with 7 billion, I only need 33 comparisons. That is binary search. I would call that pretty efficient, won't you? Okay, 33 comparisons is all that you need to find a particular entry within 7 billion. Okay, so right now, I'm going to use a little bit of time to, do you guys want to pass this around, instead of me, calling out your name? Or do you want me to call your name?
Pass it. Pass it.
Pass it? I'll just call the names for once. I will turn off the recorder because I don't want that to be recorded.